adjust whatever you need down. So we're talking about acid-base strength as a function of molecular structure, and there are two issues that have to be taken into account: series issues and group issues. When you look at your periodic table, of course, you know what series are going across and going up and down in groups. In series, the strength of the acid is based upon strength of electronegativity. So in increasing acidity, increasing electronegativity of the central element. This is just kind of a generalization. However, when you're talking about acids going down, the ability to ionize or deliver a hydrogen from a central element into solution, the strength of acid depends on size of the structure. So let me get a different color here. So I'm going to go this way. Pen's not there. We go. Size of central element defines acidity. Okay, so up and down, size, all of this right here. In series, if we have a structure, it will depend on the electronegativity of the sequence of elements. Now, let me explain that now, and so you'll have a relative understanding of what that means. Okay, so electronegative effects and acidity. Okay, acidity is the ease of delivery of hydrogen into solution. So if we look at a series, carbon, hydrogen, nitrogen, hydrogen, carbon, nitrogen, oxygen, hydrogen, and say fluoride, we'll just use fluoride as a halogen, hydrogen. We see right away that as you proceed from carbon to fluoride, we have increasing electronegativity. Well, this increasing electronegativity increases the polarity toward the central element. That will, of course, be here. So this would have a very low electronegativity end. Now, on this end would be a high electronegativity. Well, the issue of the electronegativity is that it reduces the strength of bond. So electronegativity, if the polarity is very strong, we reduces strength of bond, and that increases acidity. Okay, so that's one consideration. On the other end of the spectrum, of this sequence, we have a very low electronegativity, and it does not function to reduce the strength of the bond. So we have a strong bond between hydrogen and the carbon, so to speak, or whatever element's there. Okay? And so ionization potential is very low. And consequently, it has almost nil acidity. So in context, the thing we look at in terms of whether or not the hydrogen will break away from a given element and deliver itself into solution as an acid is the strength of bond due to electronegativity. So in a general sense, if we have, say, methane, then ammonia, and water, and then hydrofluoric acid, in that sequence, who is the strongest acid? Who is the weakest acid is the typical question that would be presented. So as we go from left to right, based on what I've just given you, we have an increasing electronegativity of the central element. That'd be fluoride in this case, oxygen in this case, nitrogen, and carbon. We have a high electronegativity here, low electronegative here, a strong bond between the hydrogen and the central element, weak bond, and as a result, poor acidity, very, 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 very weak acid. And this is a good, if you will, acidity as you move across in that context. So in series, the electronegative effects will certainly have a big play in the acidity and how easily something will break away. Also, acidity is governed by the number of electronegative elements that are attached to a given central element. If you compare, say, HClO, HClO2, HClO3, and HClO4, look at that sequence. And on the end, on the right end, on the right side of you, that is one of the strong acids. That's perchloric acids. So please keep in mind, this is a strong acid. Well, what would that tell you about the anion of that? It would be a very, very high, super high electronegativity, which would weaken the bond and make that a very strong acid. So on this right side, we have perchloric acid, and under that one strong 6. So we have a weak bond, high electronegativity. Okay, and of course that would give you a very, very strong acid. Okay, that's kind of a reference point. And as you move back to the left, everything decreases from there. See, that's the point I'm trying to get you to focus on that one molecule, because you know it's going to be a strong acid. Well, all of these are weaker acids. So in the context of trying to decide on, well, given a list on a test, say A, B, C, D, which of the following is the weakest acid? Well, of course, it'd be down here, because it has fewer electronegative structures. Here's 4 oxygens, 3 oxygens, 2 oxygens, and 1 oxygen. So it is the number of electronegative structures within a given molecule that also contributes to the acidity, because they will draw electron density away from the hydrogen, whatever it's bonded to, bond, and make it more acidic or less acidic. So your acidity, we have increasing acidity from left to right. because of increasing electronegative character. And so this would be the, right here, and you'll see this on test day 2. Please make note of this. This is a weaker conjugate base, or it'll say a weaker Bronsted base, or just simply a weaker base. In the nature of trying to define who's a strong acid, weak acid, which of the following is a weaker base? Okay, so you look at the series and you see which one has a lower electronegativity. Well, certainly that would have the weaker ability to deliver the hydrogen into solution. That's the point of issue. Okay. Now you have what is called an analogous series, which is electronegative concept in the same context. If you had, say, H, F, O, H, C, L, O, H, B, R, O, and H, I, O in consideration for a question. Okay? Who in there would be the strongest acid, and who in that collection would be the weakest acid in that context? The higher electronegativity in that would be the in the molecular structures like this would be the stronger acid, because this bond in here would be weaker than this bond in here. This was a stronger bond, weaker bond. Sorry. Wait a minute, I'm getting it backwards. Come on, JP. Stronger acid, weaker bond. I'll get my brain geared in a minute, guys. Hang on. Sorry. Like that, sorry. So, and the reason for this is that you have a decreasing electronegativity, and so that decreasing electronegativity decreases the strength of your bond if it's built in this context. Decreasing acidity. Now this is in a group, fluoride, chloride, bromide, and iodide, but it is also in a oxoacid type environment. Oxoacid environments are dependent on the electronegative characteristics. However, if you have a binary group consideration, series or group effect on acidity. Group effects on acidity depend on size of the central element. So when we're talking about the halogens, this is the easiest one to illustrate. We have H, F, H, Cl, H, Br, and Hi. Okay? Now, as you go down, you know that the electronegativity decreases down this way. However, the stronger acid is the hydrogen iodide. This is the weaker acid, and this is a stronger acid. Because of size, the electronegative effect acts to hold on to the hydrogen. So if we have a hydrogen, I'm going to do it a different way. Let's see. So here is the fluoride right here in our hydrogen. Here is the chloride right here. Here is the bromide And here is the iodide, way out here. So as you go down, the radius increases. Nuclear effects decrease. Nuclear attraction decreases. And acidity increases. And this is only fluoride, chloride, bromide, and iodide. This is called the hydrogen halide paradox. Very classic type issue, but only occurs as a result of size effect. Because the shielding effect in here of all of the internal core orbitals functions to reduce the effect of the nucleus on that hydrogen out here, and this is easy to remove on the hydrogen iodide, and therefore it is a stronger acid. And because of the closeness of the hydrogen to the fluoride nucleus, this is difficult to remove. And so this would be a weaker acid as compared to the hydrogen iodide, the stronger acid. And that contact. So that's a classic series, and I just want to share that with you in terms of its nature and how it goes. Now you can apply the same thing to the other groupings in here if you took a periodic consideration here and hung the hydrogens on. The H2S would be more acidic than water, HOH. Phosphorus trihydride would be more acidic than ammonia. It would break off easier because the central elements are bigger. So those are usually so weak anyway that they're really not even taken into account. The only ones that are really taken into account for practical reasons are the halides, hydrogen halides, and that goes, and the paradox is that it goes against the electronegativity concept. That's where the rub lies, so to speak.